We started a discussion on Carnot cycle and reversibility in the previous video, and we finished the reversibility in the previous video. We have also discussed heat engine and first and second laws of thermodynamics in previous videos as well. Now let's continue with the Carnot cycle. A reversible cycle, a completely reversible cycle, is an ideal hypothetical cycle in which all the processes, whether it's heat addition, whether it's heat rejection, or work input or work output, whatever it may be, all the processes are reversible. We discussed a reversible process before. So a cycle in which all the processes are reversible is called a reversible cycle. So for a Carnot cycle, you will have a reversible heat addition, which is a heat input, a reversible heat rejection, a reversible work input, and a reversible work output. As I mentioned in the previous video, reversible process itself is an ideal process. All actual processes are irreversible, and therefore Carnot cycle is an ideal cycle, or a reversible cycle is an ideal cycle. Excuse me. Now, what are the four processes, and how can we explain the four processes in the cycle? Now, we mentioned in a previous video that for a cycle you will have a high temperature source from where heat of Q1 is flowing into the system, and a low temperature source where you will have a heat rejection, and you will also have a work input and work output. So all these processes in the cycle, or in a reversible cycle, will be in a Carnot cycle will be reversible. Now let's see how we can constitute a Carnot cycle. So it's easy if you explain the Carnot cycle on a PV diagram. So let me constitute a PV diagram in here. Is not straight enough. Okay, now what you will have is on a PV diagram you will have an isothermal process. Isothermal process is your heat addition at a constant temperature. It's a constant temperature process. So you have a constant temperature heat addition like this. You have a let's call it 1 to 2. So you have the heat addition here, and then you will have a reversible adiabatic process, where there is only work transfer and no heat transfer. So you get your work output in the reversible adiabatic process. An adiabatic process is one where no heat transfer. We will discuss these processes later on, but for the time being you just understand how we can constitute a Carnot cycle. And then once your work output is done, then you will have a reversible isotherm once again for the heat rejection. So you will have another process which is again a reversible isotherm. So you can call the adiabatic process here, and let's call it 2 to 3. So 1 to 2 is a reversible isotherm, 2 to 3 is a reversible adiabatic, and here you have the heat rejection to a low temperature sink, and then you will have the work output, work input. So here your work output, you reject the heat, and then you will have the work input. So that is your work in. It's pump work, and this is your turbine work. So this is 3 and this is 1 again. So 1, 2, 3 and this is 3 and this is 4. So 1, 2 is a reversible isothermal where constant temperature heat addition happens, and 2, 3 is a reversible adiabatic where work is discharged with no heat transfer, and 3, 4 is another reversible isotherm where constant temperature heat rejection, you have the heat rejection to the sink here, and you have 4, 1 another reversible adiabatic where you have work input with no heat transfer. So these 4 processes all reversible. Constitute a Carnot cycle. All these 4 processes are reversible processes, and those constitute a Carnot cycle. Now this is a PV diagram of a Carnot cycle. You can also draw a TS diagram, and once again entropy is not a concept that we discussed already, so we will see the topic entropy in next few videos, and you can excuse me, on a TS diagram your Carnot cycle will simply be a rectangle, because the heat addition happens at constant temperature, and you can see T1 equal to T2 here, and your work output happens at no heat transfer. Therefore your S2 equal to S3, where S is entropy. Entropy is ds, change in entropy is dq by T. So if dq equal to 0, that means ds equal to 0, and that's why there is no change in entropy, that is S2 minus S1 or S3 minus S2 is 0, and therefore you have 2 and 3, S2 and S3 the same. And then you have isothermal heat rejection here to the sink at T2 or T3 equal to T4. So your isothermal heat rejection, and then you have your isentropic work input where you have S1 equal to S4. So these 4 processes constitute a Carnot cycle. Once again, you have 2 reversible isothermal processes and 2 reversible adiabatic processes. Isothermal is heat addition at constant temperature, and adiabatic is work input or work output with no heat rejection or absorption. So one isotherm, constant temperature heat addition, one adiabatic, work output with no heat transfer, and heat rejection at constant temperature, that is the second isothermal process, and then the second reversible adiabatic process, which is work input with no heat transfer. So these 4 processes constitute your Carnot cycle, and once again Carnot cycle is an idealization of actual processes and practically not possible. We will find out the efficiency of the Carnot cycle, and we will discuss heat engines in the next video. Thank you.